Hello students, today we shall discuss about the valence bond theory, that is the VBT, the postulates and drawbacks of VBT. Three theories were developed in order to explain the bonding and properties of coordination compounds, that is VBT, valence bond theory, CFT, crystal field theory, and MOT, molecular orbital theory. Today we shall discuss about the postulates of VBT, that is valence bond theory. Valence bond theory was proposed by Pauling and he has given some of the postulates as follows. Postulate number 1. Each central metal ion in a complex makes an adequate number of empty d orbitals for incoming d orbitals. The number of empty d orbitals made available by the central metal ion for incoming d orbitals will be equal to its coordination number. That is, if the coordination number of any central metal ion is 4, then it makes available of 4 empty d orbitals for incoming ligand. That means a 4 empty ligand can accommodate in the complex. If it is 6, the coordination number of central metal ion is 6, then 6 empty d orbitals are made available by the central metal ion for incoming ligand. And postulate number 2. Postulate number 2 state that the d orbitals in the central metal ion undergoes a process called as hybridization before bonding, before forming a coordination bond, and the orbitals or the new orbitals generated in the process called as hybridization have an equal energy, and that orbitals are called as the hybrid orbitals. In the hybrid orbitals or during a hybridization, the orbitals, d orbitals involved, sometimes it may be outer d orbitals, sometimes it may be inner d orbitals. When the hybridization involves the outer d orbitals, that is Nd, then the complex called as outer complexes. Complexes are called as the outer complexes. Whenever it involves the inner d orbital, that is n minus 1 d orbital, then they are called as the inner complexes. That is, even if for example, in a case of the octahedral complexes, the hybridization may be n minus 1 d2 sp3 or n sp3 d2. Whenever the complexes are the inner complexes, they are low spin complexes, and whenever the complexes are outer complexes, then they are the high spin complexes. You know what are high spin and low spin complexes. High spin complexes are the one which has the maximum number of unpaired electron, whereas the low spin complexes are the one which doesn't contain the unpaired electron. And when in order to form a inner complexes, that is in order to form a low spin complexes, then it should have a strong ligand. Whenever complex consists of the strong field ligand, that is strong ligand, then that particular complex always leads to a low spin complexes and inner orbital complexes. Whenever the orbitals in the complexes it contains a weak ligand, then it always leads to a formation of the high spin complexes and outer field or outer complexes. They are interconnected to each other. That is about the postulate number 3. Now postulate number 4. That is, each atom in the ligand or ligand must contain at least one orbital containing a lone pair of electrons. That is, in order to donate, in order for the donation to the central metal ion. Now, what is the meaning of lone pair electron? Lone pair of electrons are the electrons present in the they are present during the hybridization, but they are not involved in the hybridization. They are not involved in the hybridization. And postulate number 5. The empty orbitals of the central metal ion overlaps with the filled orbitals of the ligand to form the metal ligand bond or the coordinate bond. This is all about the postulates of the VBT, that is valence bond theory. That is first theory, about the coordination number, second is about the hybridization, and third is about the outer complexes and inner complexes, high spin and low spin complexes. It gives information about that. And fourth one is about the ligand, how exactly the ligand should be present. And fifth one is about the the way through which the bonding takes place. Let us study the drawbacks of the VBT. Even though VBT is an effective in explaining the bonding, but it fails to explain the reason behind the colored nature of the coordination compounds, that is, which is also called as electronic spectra or DD spectra. That is, it fails to explain why the coordination compound shows a color. If you look at into the D complexes of the D block elements, usually they are colored. They gives the color like purplish, pinkish, greenish, yellow. The best example for the complex of coordination compound is the copper sulfate, which is blue in color. But the VBT doesn't explain what is exactly the reason in order to show the color or the reason behind the color nature of the coordination compounds, but which was later explained by CFT. The second drawback of the the VBT is the correlation between the magnetic behavior and geometries is sometimes it is misleading. It doesn't explain. Even in the octahedral complexes, sometimes they are paramagnetic, diamagnetic. It doesn't explain the correlation between the geometry and magnetic behavior. You know how exactly the magnetic field is generated. I am talking about the third drawback. The magnetic field usually generated by the spin motion and orbital motion of the electron, but the VBT doesn't count or doesn't take into consideration of the orbital motion, which will be contributing for the magnetic field generated by the D block elements or the coordination compounds. That means, according to VBT, the magnetic field is generated only by the spin motion of the D electrons. It doesn't explain what about the orbital motion. What about the orbital motion of the electron, which is needed, which is contributing for the magnetic field? Actually, inner coordination compounds, the orbital motion of the d electrons of the central metal ion is quenched by the electrons of the ligand. The reason is that, but the VBT doesn't explain that. It doesn't taking into consideration. The last drawback is that central metal ion in some oxidation state, it is outer complexes or it is low spin, and in the same oxidation state, it is sometimes high spin or it is outer complexes. What is exactly the reason? Why a particular central metal ion in a particular oxidation state it shows both the high spin and low spin complexes or outer and inner orbitals, inner complexes. Why so? That is not be able to explain by the VBT. This is about the drawbacks of the VBT. I repeat once again, the first drawback of the VBT is that It doesn't explain the colored nature of the coordination compounds, and the magnetic behavior and geometry is misleading. And third one is it doesn't explain why some of the why some elements in the same oxidation state behave as both the paramagnetic and it shows both the the outer complexes and inner complexes. And the last one is that it doesn't explain why the magnetic field generated by the orbital motion has not taken into consideration. So, this is all about the postulates and drawbacks of VBT. Thank you.